Section 1. It redefined the physics of aerial combat, clocking in at speeds exceeding 540 miles per hour. Over 100 miles per hour faster than the best Allied piston fighters. To the terrifyingly vulnerable crews of B-17 bombers, the Messerschmitt Me-262 appeared not as a machine, but as a phantom, closing the distance with a violence that rendered traditional defensive gunnery obsolete. Yet behind this veneer of invincible velocity lay a catastrophic hidden variable. For every hour of adrenaline-fueled flight, the aircraft required dozens of hours of intensive, specialized surgery on the ground. The engine was not a durable power plant. It was a ticking time bomb of metallurgical failure. Now, let's open the operational records and analyze the systems that defined this campaign. The Me-262 represents the ultimate engineering paradox, a tactical masterpiece built upon a logistical house of cards. When we examine the strategic landscape of late 1944, we see a nation banking its survival on a Wunderwaffe, or miracle weapon. Yet, the defining metric of this aircraft wasn't its climb rate or its heavy autocannon armament. It was the catastrophic disparity between its performance in the air and its fragility on the tarmac. The operational logic was fundamentally broken. The Luftwaffe wasn't just deploying a new fighter. They were deploying a volatile prototype that demanded a pristine, high-tech support network while operating in the ruins of a collapsing industrial base. This was the speed trap. The very technology designed to save the Reich accelerated its resource depletion, turning the jet engine itself into a disposable munition rather than a durable component. Section 2. To understand why a system so fragile was pushed into service, we must map the strategic reality of 1944. The Allied bombing campaign was systematically dismantling German industry, and the Luftwaffe's standard piston engine fighters, the Bf-109s and FW-190s, were losing their efficacy against the dense defensive boxes of B-17s, now protected by long-range P-51 Mustang escorts. The German High Command faced a brutal calculus. Their existing attrition rate was unsustainable. They needed a technological leap to reset the board. The doctrine shifted from methodical development to panic-driven deployment. The Me-262 was envisioned as the ultimate interceptor, designed to slice through bomber streams with heavy 30mm cannons before escorts could react. The operational plan hinged on the assumption that technical superiority could override the fundamental laws of logistics. However, when we analyze the development timeline, we see a fatal deviation from standard engineering protocols. In a stable environment, a propulsion system as revolutionary as the axial flow turbojet would undergo years of stress testing. Here, the cycle was compressed into a chaotic rush. The decision was made to freeze the design of the Jumo 004 engine for mass production before its reliability issues were solved. This was the critical inflection point. The Ministry of Aviation essentially bet the farm on a prototype. We see a strategy that prioritized numbers on the ramp over hours in the air. The plan assumed that German industry could simply build its way out of the problem, replacing engines as fast as they burned out. But this ignored the logistical footprint required to move, install, and test those engines. They were building a fleet that required a pristine support infrastructure, yet they were forcing it to operate within a collapsing, fuel-starved economy. The command was to intercept the enemy at all costs, but the cost was already embedded in the engine itself. Section 3. The heartbeat of the Me-262 was the Junkers Jumo 004, a feat of engineering that was simultaneously a glimpse into the future and a prisoner of the present. To understand why this enabler became a bottleneck, we must look past the aerodynamic cowling and into the metallurgy of the combustion chamber. A jet engine is, fundamentally, a machine that converts fuel into heat and heat into thrust. This process generates extreme internal temperatures, requiring turbine blades capable of spinning at thousands of revolutions per minute while bathed in fire. In a standard engineering environment, these components would be forged from high-grade, heat-resistant alloys rich in rare earth metals like chromium, nickel, and molybdenum. These materials prevent creep, the tendency of metal to slowly deform and stretch under high heat and stress. However, by 1944, the Allied blockade had choked off Germany's supply of these strategic materials. The logistics of the raw material supply chain dictated the design of the engine. When we analyze the bill of materials for the production Jumo 004B, we see a stark metallurgical austerity. The engineers were forced to substitute high-grade nickel alloys with tiner, a mild steel with a significantly lower melting point and far less structural integrity under thermal load. This was not an engineering choice. It was a logistical surrender. To compensate for using inferior metal, the design team at Junkers pioneered a brilliant but desperate innovation: the hollow turbine blade. Instead of solid metal, the blades were formed from sheet steel, folded and welded, with a channel running through the center. This allowed cool air, bled from the compressor stage, to circulate inside the blade and keep the steel from melting. It was a technical marvel that allowed the engine to function, but it did not solve the structural weakness. It merely delayed the inevitable. When we examine the failure data, we see that while the air cooling kept the blades from instantly melting, it could not prevent the steel from suffering plastic deformation. Under the immense centrifugal force of operation, the mild steel blades would slowly lengthen, literally stretching out like taffy. This is the phenomenon of creep in its most lethal form. If the engine ran too hot or too long, the blades would stretch until they scraped against the engine casing, causing catastrophic disintegration. This metallurgical compromise transferred the burden of survival from the factory to the cockpit and the ground crew. The pilot had to operate the throttle with extreme delicacy. Pushing the throttle too quickly would dump excess fuel into the chambers before the airflow increased, creating a heat spike that would instantly cook the turbine blades. Thus, the enabler, the engine, came with a set of handling restrictions that were antithetical to combat flying. The pilot was fighting two battles, one against the Allied bombers and one against the thermal limits of his own engine. The logistical reality of the material shortage meant that the Jumo 04 was not a durable military asset. It was a consumable item, barely surviving the forces it created. Section 4. When we conduct a systems autopsy of the ME-262's operational deployment, we uncover a logistical demand signal that was not just high, it was terminal. The defining statistic of the Jumo 004 engine was its mean time between overhaul, MTBO. In a mature aviation system, an engine might run for hundreds of hours before requiring major intervention. For the Jumo 004, the official service life was theoretically 25 hours. In reality, under combat conditions with inexperienced pilots utilizing rapid throttle adjustments, the operational life often collapsed to just 10 hours. We need to pause and process the gravity of that number. 10 hours. If a single mission lasted roughly 45 minutes to an hour, the Luftwaffe was effectively losing an engine every 10 sorties. This created a logistical consumption rate that no supply chain in history could sustain, let alone one under constant aerial bombardment. When we plot the data, we see the demand curve going vertical, while the capacity line remains flat or declining. This wasn't maintenance. It was a continuous cycle of replacement. The aircraft became a parasite on its own ground crew. The workflow on the tarmac reveals the severity of this friction. Changing a Jumo 004 was not a simple field swap. It was a complex surgical procedure requiring heavy lifting gear, specialized tools, and most critically, highly trained personnel. You could not assign a standard airframe mechanic to a turbojet. The tolerances were too tight, the fuel connections too volatile. The engine required precise alignment and rigorous ground testing before the pilot could trust it with his life. This introduced a critical bottleneck: human capital. As the war of attrition ground down the Luftwaffe, the pool of expert mechanics vanished. We see a system trying to service space-age technology with a depleted, exhausted workforce. Reports indicate that incoming replacement engines often arrive from dispersed underground factories with significant manufacturing defects, misaligned turbine wheels, or poor welding, due to the reliance on forced labor and the chaos of the supply lines. This meant the frontline mechanics weren't just installing engines, They were essentially rebuilding them in the field, further driving up the man-hours required per flight hour. The logistical footprint of the Me-262 effectively grounded it. Because the engines were so temperamental and required such specific infrastructure, the jets were tethered to long concrete runways at major bases like Akmer and Rhine. They lacked the operational mobility of the piston fighters, which could operate from grass strips. This geographic rigidity allowed Allied commanders to counter the jet not in the air, but on the ground. By mapping the logistical nodes, the specific airfields capable of supporting the jets, Allied fighters could swarm these locations. Furthermore, the engine's spool-up time, a direct result of the fragile turbine blades described earlier, created a tactical vulnerability rooted in logistics. Because the pilot could not slam the throttle forward without melting the engine, the aircraft was helpless during takeoff and landing. It was a sitting duck, requiring protection from piston engine fighters just to get into the air. Here, the system completes its breakdown. The miracle weapon required its own bodyguard. By early 1945, we see the ultimate inversion of the supply chain. Operational records show rows of brand new Me-262 airframes sitting idle on the tarmac, fully armed and ready for war, but lacking functional engines. The airframes were durable. The propulsion was disposable. The system had achieved a capacity of 0 because the flow of spare parts could not match the burn rate of the turbines. The Luftwaffe had built a Formula One car but tried to run it with the logistics of a demolition derby. The breakdown was total. The weapon didn't fail. The loop that sustained it did. Section 5. When we render a final verdict on the Me-262 program, we are left with a stark illustration of the difference between capability and availability. The operational records confirm that while the jet was a tactical triumph, possessing the raw power to alter local skirmishes, it was a strategic catastrophe. The system failed not because the aerodynamics were flawed or the pilots lacked skill, but because the logistical cost of operation was higher than the combat value returned. The Me-262 was a weapon that consumed its own infrastructure. The Jumo 04 engine serves as the ultimate cautionary tale in systems engineering, the danger of decoupling performance from reliability. The German High Command fell into the trap of looking only at top-line metrics: speed, climb rate, and firepower. They ignored the bottom-line metrics: serviceability, mean time between failures, and supply chain maturity. By pushing immature technology into mass production, they created a fleet that was effectively born grounded. The lesson here is timeless and brutal. Reliability is not a luxury. It is a performance specification. In modern supply chain terms, the Me-262 suffered from a fatal lack of resilience. A robust system can absorb shocks. A fragile system shatters under them. By building a jet that required high-precision parts and expert labor in an environment that lacked both, the Luftwaffe engineered a single point of failure into every aircraft. They proved that you cannot innovate your way out of a logistics crisis if that innovation increases the logistical burden. The enabler, the jet engine, became the anchor that dragged the entire operation to a halt. As we close the file on the Me-262, the roar of its engines fades, leaving us with a silent, enduring truth. Innovation is seductive, but without a foundation of resilient logistics, it is merely a spectacle. The most advanced system in the world is useless if the chain that sustains it is broken. In the end, the outcome wasn't decided by who flew the fastest, but by who could keep flying the longest.